The glass in your window appears perfectly still. You can tap it, hear the sharp ping against its surface, and feel its cool, solid resistance against your fingertips. For all practical purposes, it seems frozen in time, a material locked in permanent stasis. Yet what if I told you that this seemingly motionless substance might actually be moving right now? That the window panes in your home, the drinking glasses in your kitchen cabinet, and the screen on your smartphone might all be imperceptibly flowing like extremely slow-motion honey? This isn't science fiction or some esoteric thought experiment. This is the glass flow paradox, a scientific mystery that has puzzled physicists, materials scientists, and chemists for centuries. Look around you. Count how many glass objects you can see from where you're sitting. Each one might be engaged in an invisible dance of molecular rearrangement so gradual that generations of human observers would notice no change. Medieval cathedral windows that appear thicker at the bottom than at the top once sparked the theory that glass flows downward over centuries due to gravity. This captivating idea persisted in scientific textbooks until relatively recently. But is it true? The answer takes us into the strange borderlands between solid and liquid states of matter, where time itself seems to stretch and compress in ways that challenge our intuition. The glass in ancient buildings does indeed sometimes appear uneven, with variations in thickness that suggest movement over time. In 1945, a scientist measuring windows in European cathedrals noted this phenomenon and proposed the flow theory that would become scientific orthodoxy for decades. The explanation seemed elegant and intuitive. Glass, while apparently solid, must be an extremely viscous liquid that flows so slowly we cannot perceive its movement within a human lifetime. Only across centuries would the effects become visible, a material caught in an endless state of becoming, never quite reaching equilibrium. This narrative satisfied our human tendency to seek patterns and explanations. It also carried a poetic quality that transcended mere science. The idea that something could appear completely static to our senses yet be in constant, imperceptible motion. But like many beautiful theories, it eventually collided with a more complex reality. Modern material science has challenged this simple explanation, revealing a story far more fascinating about the nature of glass, time, and the states of matter that we thought we understood. The journey into this mystery takes us from medieval cathedrals to modern laboratories, from the atomic structure of silicon dioxide to philosophical questions about permanence and change. It requires us to examine not just what glass is, but what it means for something to be solid or liquid in the first place. And as we will discover, the truth about whether glass flows is not just a matter of scientific fact. It opens a window into how we perceive reality itself, and how materials we take for granted might be engaging in processes that operate on timescales we can barely comprehend. To understand the glass flow controversy, we first need to travel back to its origins. The story begins not in a laboratory, but in the workshops of medieval glassmakers in Europe between the 12th and 17th centuries. These artisans created the spectacular stained glass windows that still adorn cathedrals from Notre Dame to Canterbury. Working with primitive tools and techniques passed down through generations, they produced glass through a process that was part science, part art, and part mystery. Nicholas Abbott, a materials historian at the University of Cambridge, has spent decades studying medieval glassmaking techniques. The crown glass method was predominant, he explains, demonstrating with his hands the spinning motion used by ancient craftsmen. Molten glass would be gathered on the end of a blowpipe, blown into a bubble, transferred to a pontil rod, and then spun rapidly. Centrifugal force would cause the glass to flatten into a disc up to a meter in diameter. These discs, called crown glass, had characteristic features. They were thicker around the edges and at the center, where the pontil rod attached, and thinner in between. When cut into panes for windows, the glass naturally varied in thickness. Glassmakers would typically install these panes with the thicker edge at the bottom for stability, a practical decision that would later be misinterpreted as evidence of flow. The earliest scientific observation of this phenomenon appears in the notes of George Christoph Lichtenberg, an 18th-century German physicist. During a visit to a Gothic cathedral in 1782, he observed, "The glass panes in very old buildings, particularly churches, are often thicker at the bottom than at the top. This suggests that glass, over extremely long periods, behaves as a fluid rather than a solid." Lichtenberg's casual observation would remain a scientific curiosity for nearly 2 centuries until 1945, when American scientist Edgar D. Zanato published what would become a seminal paper titled, "Do Cathedral Glasses Flow?" His measurements of windows in European churches built between 1100 and 1500 CE showed consistent patterns of thickening toward the bottom. Zanato calculated that if glass were flowing, its viscosity, resistance to flow, would need to be approximately 10 to the power of 23 poises, a number so vast it defies everyday comparison. To put this in perspective, water has a viscosity of about 0.01 poises, honey around 100 poises, and pitch, used in the famous long-running pitch drop experiment, about 10 to the power of 8 poises. If cathedral glass were flowing at Zanato's calculated rate, it would take approximately 10 million years for a pane to show noticeable sagging. Despite these extraordinary timescales, the idea captured scientific imagination. Throughout the mid-20th century, the concept that glass is a supercooled liquid appeared in chemistry and physics textbooks. It offered a tidy explanation for the observed phenomenon and aligned with certain theoretical understandings of amorphous materials. The glass flow theory had become scientific conventional wisdom, but science advances through questioning, not consensus. By the late 1990s, researchers had begun to challenge this elegant explanation. Pamela Ostendorf, a glass physicist at Cornell University, led a team investigating the composition and microstructure of medieval cathedral glass using advanced spectroscopic techniques unavailable to earlier scientists. "What we discovered completely upended the flow narrative," Ostendorf recalls. "The variations in thickness had nothing to do with flowing glass and everything to do with the manufacturing process. The medieval crown glass method inherently produced panes with variable thickness, and the craftsmen consistently installed them thicker side down for purely practical reasons." Further analysis of cathedral windows revealed another crucial piece of evidence. Horizontal panes that had been in place for centuries showed the same thickness variation from edge to center. If gravity were causing flow, horizontal panes should show different patterns than vertical ones. They did not. The elegant theory of flowing glass in cathedral windows was crumbling. But this didn't settle the larger question. Does glass flow at all? To answer that, we need to venture into the molecular structure of glass itself and the fundamental physics of what makes something a solid, liquid, or something in between. When most people think of glass, they imagine the silica-based material in windows and drinking vessels. But glass actually refers to a broader state of matter. Any non-crystalline solid that exhibits a glass transition when heated. This includes not just window glass but materials like amber, many plastics, certain metals, and even some biological substances. What makes glass unique among solids is its atomic structure. Most solids are crystalline, meaning their atoms arrange in ordered, repeating three-dimensional patterns. Think of a crystal as a perfectly organized library where every book has its designated position. Glass, however, lacks this orderly arrangement. Its atoms form an irregular network without long-range periodic structure, more like books haphazardly stacked with no system. This disordered structure results from how glass forms. When most materials cool from a liquid state, their molecules slow down, settle into ordered crystal arrangements, and solidify at a specific freezing point. But glass-forming materials cool differently. As they lose heat, their molecules move more sluggishly but never organize into a crystalline structure. Instead, they gradually become more resistant to flow until the material becomes rigid, yet maintains its disordered molecular arrangement. This process, the glass transition, differs fundamentally from crystallization. There's no abrupt phase change where the material suddenly becomes solid. Instead, the liquid becomes increasingly viscous until molecules move so slowly that, for practical purposes, the material behaves as a solid. This peculiarity led Nobel Prize-winning physicist Philip Anderson to call glass the deepest and most interesting unsolved problem in solid-state theory. The glass transition temperature, TG, marks where a material transitions from a flexible, rubbery state to a brittle, solid-like state. For window glass, soda-lime glass, this temperature is around 550 degrees Celsius, 1022 degrees Fahrenheit. Above this temperature, the material can flow. Below it, the material appears solid. But unlike the freezing point of water or the melting point of metal, the glass transition isn't a sharp boundary. It's a gradual change occurring across a temperature range. This ambiguous transition feeds the fundamental question: is glass technically a solid or an extremely slow-flowing liquid? The answer depends partly on how we define these states of matter and partly on the timescales we consider. Professor Nathan Ashcroft, director of the Glass Research Institute at MIT, explains it this way: from a practical engineering perspective, glass at room temperature is unquestionably a solid. It has definite volume and shape, resists deformation, and breaks rather than flows when sufficient force is applied. These are the classical properties of solids. However, he continues, from a thermodynamic perspective, glass exists in a non-equilibrium state. Its molecules are arranged as they were in the liquid phase, just moving extremely slowly. This is why some physicists describe glass as a frozen liquid or an amorphous solid. Both descriptions capture some aspect of its nature. This thermodynamic ambiguity leads to the central question about glass flow. If glass exists in a non-equilibrium state with liquid-like molecular arrangement, might it continue to flow, however slowly, even at room temperature? To investigate this possibility, scientists needed to measure or calculate glass viscosity at room temperature. A challenging task given the extraordinarily slow molecular movement involved. The most famous experiment attempting to measure the flow of an extremely viscous substance isn't actually about glass at all, but about pitch, a derivative of tar. The pitch drop experiment, started in 1927 by Professor Thomas Parnell at the University of Queensland, demonstrates the flow of an apparently solid material over long timescales. A sample of pitch in a funnel has produced only 9 drops in nearly a century, indicating a viscosity approximately 230 billion times that of water. Yet pitch is still flowing measurably faster than any potential flow in glass. For actual glass, direct observation of flow at room temperature would require timeframes far beyond human lifespans. Scientists have therefore turned to theoretical calculations, computer simulations, and indirect experimental evidence to address the question. In 1998, physicist Edgar Zanato published a pivotal paper that examined how long it would take for window glass to flow noticeably at room temperature. Using calculations based on glass's molecular structure and the principles of statistical mechanics, he estimated that a significant deformation would take approximately 10 to the power of 32 years, a time span vastly longer than the age of the universe, approximately 13.8 billion years. To put this in perspective, Zanato wrote, "If the universe itself were made entirely of window glass, we wouldn't expect to see noticeable flow before the end of the universe as we know it." This calculation seemed to settle the matter. While glass might theoretically be capable of flow, the timescales involved made it practically impossible under normal conditions. Glass, for all human purposes, behaves as a solid. But the story doesn't end there. As often happens in science, new research and more sophisticated techniques have revealed additional layers of complexity to the glass flow question. These developments force us to reconsider not just whether glass flows, but what it means for any material to be truly solid. The deepening mystery of glass flow took a fascinating turn in the early 2000s when research teams around the world began examining glass at nanoscale levels using advanced atomic force microscopy and nuclear magnetic resonance spectroscopy. These techniques allowed scientists to detect molecular movements too subtle to observe with previous methods. Dr. Penelope Orion, a physicist specializing in amorphous materials at the California Institute of Technology, led one of these groundbreaking studies. Her team examined ultra-thin films of various glass types under precisely controlled conditions, measuring atomic displacements over periods ranging from hours to several years. What we found challenged the conventional wisdom that room temperature glass is effectively motionless, Dr. Orion explains. Our measurements revealed subtle but detectable molecular rearrangements occurring even at temperatures far below the glass transition point. These movements aren't uniform, flowing in one direction like a liquid under gravity, but rather localized relaxations, atoms and molecules finding more energetically favorable positions. This phenomenon, known as structural relaxation or physical aging, occurs because glass forms in a non-equilibrium state. When glass is cooled from its molten state, its molecules don't have time to find their optimal positions before becoming effectively frozen in place. Over time, these molecules can undergo minute shifts toward more stable arrangements. The discovery of these nanoscale movements revitalized the glass flow debate. While not constituting flow in the conventional sense of liquid movement, these molecular rearrangements demonstrated that glass isn't as static as previously believed. The boundaries between solid and liquid states became even more blurred. Further complexity emerged from research into a phenomenon called the Cosman paradox, named after Walter Cosman, who identified it in the 1940s. This thermodynamic puzzle concerns what happens to glass-forming liquids as they cool toward what's called the Cosman temperature, a theoretical point where the entropy of the supercooled liquid would become less than that of the crystalline solid, which violates the third law of thermodynamics. Before reaching this paradoxical state, however, the glass transition intervenes, dramatically slowing molecular motion. But the proximity to this theoretical limit suggests that glass at room temperature exists in a peculiar thermodynamic state, one that continues to drive extremely slow structural changes over time. Professor Ashcroft elaborates. The Cosman paradox implies that glass is perpetually trying to reach an equilibrium state it can never achieve under normal conditions. This thermodynamic driving force may result in measurable effects over extremely long timescales, even if we can't call it flowing in the conventional sense. Adding another layer to the mystery, researchers discovered that certain environmental factors can significantly affect glass's behavior over time. Exposure to moisture, temperature fluctuations, mechanical stress, and even ultraviolet radiation can accelerate structural changes within glass. A team at the University of Tokyo demonstrated that glass samples exposed to varying humidity levels showed different rates of surface modification over time. These changes weren't due to traditional flow but rather to surface reactions and localized rearrangements of silica tetrahedra, the basic structural units in silicate glasses. Glass is far more dynamic than we once thought, says Dr. Orion. While it doesn't flow like honey or water, it undergoes complex evolution at the atomic level in response to its environment. The question isn't really whether glass flows, but rather what types of molecular motion occur in glass and on what timescales. This reframing of the question leads us to one of the most fascinating aspects of the glass flow debate: the role of observation timescales in defining states of matter. As physicist Eugene Stanley famously remarked, glass forces us to reconsider how we define solidity itself. When we observe materials, our human perception operates on a specific timescale, seconds, minutes, hours, or at most years. But many natural processes operate on timescales vastly different from human experience. Mountains erode over millions of years, continental plates drift at rates measured in centimeters per year, and radioactive isotopes decay over millennia. In this context, the distinctions between solid, liquid, and other states of matter become partly dependent on the observer's timeframe. Materials that appear solid on human timescales might behave as liquids over geological timescales. Conversely, some materials we consider liquids might appear solid if observed over microseconds. Professor Jennifer Maxwell, a philosopher of science at Princeton University, points out that this relativity of observation creates interesting epistemological questions. Our classification of matter into discrete states, solid, liquid, gas, plasma, reflects not just objective physical properties but also the relationship between those properties and our human-scale perception. Glass challenges these classifications because it operates at the boundaries of our observational frameworks. This perspective suggests that the question, "Does glass flow?" might be better replaced with, "On what timescale does glass exhibit fluid-like behavior?" The answer involves multiple timescales of molecular motion within glass, from femtoseconds, 10 to the power of -15 seconds, to potentially billions of years. At the shortest timescales, atoms in glass vibrate rapidly around their average positions, similar to atoms in any material above absolute zero. These vibrations occur in femtoseconds to picoseconds. At slightly longer timescales, nanoseconds to microseconds, groups of atoms may undergo collective movements, particularly in regions with higher free volume or mobility. Moving to human observable timescales, seconds to years, glass exhibits elastic behavior. It deforms slightly under stress and returns to its original shape when the stress is removed, just like conventional solids. But over decades to centuries, processes like structural relaxation, phase separation in some glass compositions, and surface reactions become measurable. Finally, at geological timescales, millennia to millions of years, theoretical calculations suggest that certain types of glass might exhibit extremely slow viscous deformation under constant stress, though still at rates too minimal to be practically significant. This multi-timescale perspective helps explain why the glass flow debate has persisted. Different scientific disciplines observe glass through different temporal lenses, leading to seemingly contradictory characterizations of the same material. Materials engineers working with glass for practical applications treat it as a solid with well-defined mechanical properties. Chemists studying glass surfaces may observe reactive behavior more characteristic of non-equilibrium systems. Geologists examining natural glasses like obsidian over archaeological timescales might detect subtle compositional changes suggesting long-term molecular mobility. The turning point in our understanding of glass flow came not from resolving these contradictions but from embracing them as essential to glass's nature. Glass challenges our categorical thinking about states of matter, forcing us to adopt more nuanced, context-dependent definitions. In 2017, a collaborative research project between materials scientists and theoretical physicists at multiple institutions proposed what they called the dynamic heterogeneity model of glass. This model, now gaining widespread acceptance, describes glass as containing regions of varying molecular mobility, some areas where atoms remain relatively fixed and others where atoms have greater freedom to rearrange. These mobile regions aren't fixed in location but shift throughout the material over time. The distribution and behavior of these regions depend on the glass's composition, thermal history, and environmental conditions. The model explains many previously puzzling properties of glass, including why it can simultaneously exhibit solid-like rigidity and gradual structural evolution. The dynamic heterogeneity model represented a paradigm shift, explains Professor Ashcroft. Instead of debating whether glass is a solid or an extremely viscous liquid, we now understand it as a material with spatially and temporally varying dynamics. Some regions might exhibit liquid-like molecular rearrangements while others remain solid-like, and these regions change over time. This breakthrough has practical implications far beyond settling an academic debate. Understanding glass's complex, time-dependent behavior enables engineers to design more durable glass for specific applications, from smartphone screens that resist cracking to nuclear waste containment vessels that must remain stable for thousands of years. The glass industry now deliberately manipulates this dynamic heterogeneity through processes like ion exchange, creating Gorilla Glass and similar products, controlled crystallization, producing glass ceramics, and thermal annealing, reducing internal stresses. These techniques essentially work with, rather than against, glass's unique properties. Beyond practical applications, the revised understanding of glass flow has profound implications for how we think about materials science, time, and the limitations of human perception. It reminds us that the categories we create to understand the physical world are often simplifications of more complex realities. The glass in your window might not be flowing in the way early scientists imagined, with gravity gradually pulling it downward over centuries. But it's also not completely static at the molecular level. It exists in a fascinating intermediate state, solid for all practical human purposes yet undergoing subtle structural evolution invisible to the naked eye. This recognition of glass's complex nature extends to many other materials previously classified as either definitely solid or definitely liquid. Amorphous metals, certain polymers, colloids, gels, and even some biological tissues share similar time-dependent properties. The science of soft matter, materials that respond to weak forces or thermal fluctuations, has grown partly from insights gained through studying glass. As we deepen our understanding of these materials, we're developing new language and frameworks that transcend traditional state classifications. Terms like viscoelastic, dynamically arrested, and kinetically constrained acknowledge the role of time and observation scale in material behavior. These developments have philosophical implications as well. The glass flow question forces us to confront the limitations of human perception and the artificial boundaries we create to organize natural phenomena. Just as quantum mechanics challenged our intuitive understanding of particles, and relativity transformed our conception of space and time, the science of glass challenges our intuitive categories of solid and liquid. In a sense, glass teaches us humility, reflects Professor Maxwell. It reminds us that nature doesn't always fit neatly into the conceptual boxes we create, and that our perception of physical reality is inescapably linked to our human timescale of observation. This perspective invites us to consider how many other aspects of reality might operate on timescales inaccessible to direct human experience. Processes too fast or too slow for our senses to register without technological assistance. It encourages a more dynamic view of the seemingly static world around us. The implications of our evolving understanding of glass extend far beyond material science into unexpected domains. Neurobiologists have drawn parallels between glass dynamics and certain aspects of brain function. Computer scientists developing new memory storage technologies have leveraged insights from glass physics. Even some theories in cosmology use glass-like phase transitions to explain properties of the early universe. Perhaps most significantly, glass has become a powerful metaphor for systems that exhibit history-dependent behavior, systems whose current state depends not just on present conditions but on the path taken to reach those conditions. Economic markets, ecological systems, and social institutions all share this property, making the science of glass relevant far beyond laboratory walls. As we continue to refine our understanding of glass flow, we're developing increasingly sophisticated techniques to measure and predict extremely slow material changes. Advanced computational methods now allow scientists to simulate glass dynamics over timeframes impossible to observe directly. Artificial intelligence algorithms can identify subtle patterns in experimental data that might indicate ongoing structural evolution. These methods are revealing that different glass compositions exhibit vastly different long-term behaviors. While the silica-based glass in your windows might remain effectively unchanging for millions of years, some metallic glasses show measurable structural relaxation over decades, and certain organic glasses, like those used in pharmaceutical preparations, can change significantly over just months or years. Understanding these variations is crucial for applications where long-term material stability is essential, from preserving artistic and cultural artifacts to storing hazardous waste to designing implantable medical devices. The question isn't simply whether glass flows, but which glasses might change over what time frames and under what conditions. Contemporary glass scientists have largely moved beyond the simplistic debate about whether glass is a solid or a supercooled liquid. Instead, they focus on characterizing the specific types and rates of molecular motion in different glass formulations under various conditions. This more nuanced approach has enabled significant technological advances in engineered glasses with precisely controlled properties. Professor Ashcroft summarizes the current scientific consensus. Today, we understand glass as a non-equilibrium material with time-dependent properties that vary with composition, thermal history, and environment. It's neither a conventional solid nor a conventional liquid, but rather a distinct state of matter with its own complex physics. The old debate about whether cathedral glass flows downward over centuries has been replaced by much more sophisticated questions about molecular mobility at different length and time scales. This evolution in scientific understanding reminds us that progress often comes not from answering old questions definitively, but from reframing those questions in more productive ways. The glass flow debate didn't end with a simple yes or no answer, but with a richer conceptual framework that accommodates glass's complex reality. As we apply these insights to develop new glass technologies, from ultra-thin flexible displays to self-healing glass surfaces to optical fibers that maintain precise properties over decades, we're leveraging the very characteristics that once seemed paradoxical. The seeming contradiction between glass's solid-like and liquid-like aspects has become a source of technological innovation rather than scientific confusion. This story of scientific progress offers lessons beyond material science. It demonstrates how seemingly simple questions can reveal unexpected complexity, how overturning conventional wisdom can lead to deeper understanding, and how embracing nuance rather than seeking definitive categorization can advance knowledge. The glass in your window, the screen you might be reading this on, the fiber optic cables carrying information across global networks, all contain materials that exist in this fascinating borderland between conventional states of matter. They represent not just technological achievements but reminders of the rich complexity hidden within seemingly ordinary substances. The next time you look through a window or hold a drinking glass, consider that you're interacting with a material that has transformed human civilization, from the first crude glass beads created thousands of years ago to the sophisticated engineered glasses enabling modern technology. And while that glass might not be flowing in the way early scientists imagined, its molecular structure continues a subtle dance of atomic rearrangements, imperceptible to human senses but revealed through the patient work of scientific investigation. Glass challenges us to expand our temporal imagination, to consider processes occurring on timescales vastly different from human experience. It reminds us that seemingly solid reality contains hidden dynamics, that stability and change coexist at different scales, and that our categories for understanding the physical world are human constructs that nature doesn't always respect. In the end, the question of whether glass flows reveals more about the limitations of human perception and categorization than about glass itself. The material hasn't changed, it has always behaved according to the same physical principles. What has changed is our understanding, as we've developed more sophisticated tools, theories, and perspectives. Perhaps this is the most valuable insight from the glass flow controversy. Scientific progress often comes not from settling debates with simple answers but from recognizing when our questions themselves need reformulation. The best science doesn't just solve puzzles but transforms how we frame those puzzles in the first place. Glass, with its transparent appearance yet opaque scientific complexity, continues to serve as both a practical material and a profound metaphor. It stands as a reminder that the world around us is richer and more dynamic than our everyday perception suggests, that within apparently static reality lies constant change, occurring on timescales we can barely comprehend. The next time you touch a glass surface, consider that between your fingertip and the glass molecules lies an entire universe of physical processes operating across vastly different timescales, from the near-instantaneous electromagnetic repulsion preventing your finger from passing through the material to the potentially geological-scale structural relaxation occurring within the glass itself. In that moment of contact, you're interacting with processes spanning femtoseconds to millennia, all coexisting in a material we often take for granted. Perhaps most remarkable is how this scientific journey has transformed our relationship with time itself. We've come to recognize that apparent permanence often masks imperceptible change, that stability is frequently a matter of timescale rather than absolute stasis. In a universe of constant flux, our perception captures only a narrow window of temporal reality, a limitation that glass, with its ambiguous position between solid and liquid states, helps us recognize. While cathedral glass may not flow downward as once believed, the glass in our world exists in a state of perpetual becoming, moving toward equilibrium at rates too slow for human perception, yet following the same fundamental physical principles that govern all matter. This reality invites us to see the world not as fixed and static, but as dynamic and evolving across timescales extending far beyond our direct experience. A perspective that transforms how we understand not just materials, but time itself.